Hey everyone, this is Mohammed Nadeem and welcome to my YouTube channel. Today in this video, we will discuss electric potential energy and potential due to a point charge. So before starting the video, let's discuss the concept of potential difference and potential at a specific point. So here we have simulation. In this simulation, we have this positive charge, and if we bring that positive charge here to the lab, and if I release it, a large number of electric field lines will originate from this positive charge, and these electric field lines will be present up to a region from this positive charge up to which the effect of this positive charge is present, and that region is called the electric field around this positive charge. And inside that field, we have potential, which is given by this potentiometer. So here I'm going to label the potential at this point. At this point, the potential is given by 2.4 volt. And similarly, if I bring this potentiometer toward the positive charge, and I'm going to label here the potential is 3.4 volt. By further decrease the distance between this potentiometer and the charge, here at this point the potential becomes 8.1 volt. So from here I can say that the potential is increasing when we come near to this positive charge. So here it increased from 2.4 towards 3.4, and then it becomes 8.1 volt. And if someone asks you to find the potential difference between these 2 points, let's consider this is point A and this is B. And if someone asks you to find the potential between point A and point B, then the potential difference is given by VB minus VA. And simply put the value of VB, which is 8.1 volt minus VA 3.4 volt. And this is the potential difference. Now, in physics, we say that there is no concept of potential, but we have the concept of potential difference. So the potential difference is given by, in that case, it was potential difference at B minus potential difference at A. But in physics, there is no concept of potential, a potential at a single point. There is no concept, because potential is actually the work done per unit charge, and for a specific fixed point, the work done will be zero, because here the displacement is zero. So in this case, at specific point here, this is a specific fixed point from the positive charge. This is the fixed point from the positive charge, and also this is a fixed point, and also this is a fixed point. Then according to definition, potential difference is actually the work done per unit charge. But here work done is given by F dot S divided by charge. In this case, this for a fixed point, this S will be zero, because for a fixed point, the distance or displacement covered will be zero. So in this case, the F multiplies 0 divided by Q. In this case, the voltage becomes 0. So according to the definition of voltage, the voltage must be 0 at every point here. According to the definition, the voltage will be 0. But here, then how, if the definition say that the voltage is 0, then it's okay. Then how this potential meter show the detection? So here it shows this 2.3 volt, and it shows the voltage for a specific point. Here this point, for this point there is a voltage, but according to the definition, it said that the voltage will be 0, because here the force, the displacement is 0. So in order to handle this problem, we are going toward this topic, which is the electric potential energy and potential due to a point charge. So in order to find the potential for a specific point, here for this point, in order to find this potential, so to find the potential at a specific point, we must consider the second point at infinity. So in order to find the potential at this point here at point B, we will have to consider the second point uh, at infinite distance from this point. This point is actually come in the electric field of this positive source charge. But if we find the electric field at that point, we will consider the second point at infinity here. So if we, as we know that if we come near to the positive charge, the voltage will increase. So here, away from the positive charge, it was 2.4, and if we come near, it 3.4 and become 8.1. So if we going away from this positive charge, the voltage will decrease. So here, in this case, we can say that the voltage will decrease if we go away from the source charge, and if we move up to a distance which is at infinity, then we can say that the voltage at this infinite distance will be zero here, tends to zero, because this voltage is decreasing from this source charge. If we go away from this positive charge, this voltage is decreasing, and if we reach the infinite distance from this positive charge, then this voltage becomes zero. And the definition, the formula for that potential at point this B is equal to the work done per unit charge. So here is test charge, the work done per unit charge. But in this case, we consider the second charge at infinity. So in this case, we can say that the work done in infinity, it is at point A. So we can say that the work done from point A to point B, the work done from point A to point B divided by the charge. So that will be the potential here. So this is the equation 1. For this equation 1, we need to find this, which is the work done from this point A to this point B. So in order to find the work done from this point A to point B, we will have to convert the distance between this point A and point B into a small steps. So here is the step 1. This is actually, we have step 1, this is step 2, and this is step 3, and this is step 4. And if we take the n steps, then we will reach to this point B. So here, this is the work done will be divided into these steps. So for the first step, we can write this from the RA to R1. The work done will be from the RA to R1. So this is the work done for this step. And for this second step, for this second step, we can write that the distance, the work done is actually from the R1 to R2. These R1, R2, R3 are nothing but these are actually the distance up to that step. So here, in this case, we have RA, which is the distance between this positive charge and this test charge, this source charge and this test charge. If I take one step, then that the distance between this source charge and this first step will be R1, and if I take the second step, the distance between this source charge and this second step will be R2, and for the third step it become R3, and that's going up to Rn step, and then after Rn step we will reach Rb. So Rb is actually the distance from this source charge to the point at which we are going to find the potential. So here we divide this this work done into small steps. So for first step, the work done is this, and for the second step it's this, and for the third step, so here we have the third step. So for this third step, the work done become the work done from the R2 to R3. And in this way, we take a large number of steps, and then we will reach Rn. Rn is the second last step toward this Rb, so this is actually Rn. And then we will find the work done for here. So the work done for this last step is given by the work done from the Rn to Rb. And now the work done from A to B, the work done from this point A to B is given by work done from A to B is equal to the work done from the first step, which is actually the work done from RA to R1, which is this work done from RA to R1 plus the work done from the second step, which is this. The work done from the second step is given by the work done from R1 to R2, R1 to R2 plus the work done for the third step is work done from R2 to R3. And in this way, we will take large number of steps and then we will reach to this last step. So for this last step, the work done is written as the work done from this Rn to Rb, the work done from Rn to Rb. So this is the work done from A to B. Now we will find, this is actually equation 2. Now we will find the work done from RA to R1, then this and then this, and we'll add all these, and then we will find the work done from RA to RB, and then we will put that here, and we will take the result, the required result. So in order to find the work done from RA to R1, the work done in this case is equal to F dot del R. So this is the work done. Del R is the distance and F is the force exerted on that. The force is exerting against the field of the source charge. Therefore, I put the negative sign here. Now this become minus F del R cos theta, because this is the dot product. Now for the theta here is 180, so this will become work is equal to minus F del R cos 180, and cos 180 is equal to minus 1, so work done is equal to minus F for del R minus 1, and minus 1 and minus multiply, it become F del R. This is equation 2. Now we know that the electric field intensity is given as the electric the electric field intensity, the electric field intensity is given by E is equal to force per unit charge. So from this we can write that F is equal to E and Q. This is equation 3. Put the equation 3 in 2. So here put the value of F in equation 2. So the equation 2 become work done is equal to F. Instead of F we put this value E, Q, and this del R come in its own position. Now the value of E, this is equation 4. The value of E is given as we discussed in the previous video. E is given as E is equal to 1 over 4 pi epsilon naught, 1 over 4 pi epsilon naught Q by R square. This is the value of electric field intensity. Let's say this is 5. Put the value of electric field intensity here. So that equation, this work done equation will become equation 4. So here the work done is equal to, instead of this E, I will put this, so which is 1 by 4 pi epsilon naught and Q by R square, and this then multiply by Q and then multiply by del R. So this is equation 6, and the equation 6 is general equation for the work done. The equation 6 is a general equation for this work done. Now we will specify this equation for this smart step, and then for this, and then for this smart step, and going up to the last step. For this equation 6, for the first step is given, is the first step is actually the work done from RA to R1, which is given by this equation, which is equal to 1 over 4 pi epsilon naught Q, this Q divided by R square. This capital Q is the source charge and this Q is the test charge, and multiply by del R. So this is the equation for the work done from RA to R1. So here I will put the values for del R and R2. So here the work done from RA to R1 is given by 1 over 4 pi epsilon naught and Q, and this Q multiply del R by R square. So here we have del R. In this case, the del R is RA minus R1. This is the first step. So for the first step, del R is RA minus R1. So work done from RA to R1 is equal to 1 by 4 pi epsilon naught. So Q and Q. So this, instead of this del R, we can write RA minus R1 divided by, this is R square, and R square is actually multiplication of R and R. So in this case we can write RA R1. So for further simplification, RA minus R1, so work done from RA to R1 is equal to Q by 4 pi epsilon naught and RA divided by RA R1 minus R1 divided by RA R1. So here this RA and RA will cancel, and it will give us so the work done from RA to R1 is equal to Q by 4 pi epsilon naught, and here this RA and RA will cancel, which is equal to 1 over R1 minus this R1 and R1, this R1 will cancel, it become 1 over RA, and this is the equation 7. So the equation 7 is actually the work done from this RA to this R1. Now we will find the work done from this R1 to R2. So the next step is to find the work done from R1 to R2. The work done from this R1 to R2. The work done from R1 to R2, which is equal to, from this general equation, 1 by 4 pi epsilon naught. So this is actually Q and Q, and only the changes will occur in this del R and the below R square. So here Q by 4 pi epsilon naught, and this del R in this case is now R1 minus R2. So here it becomes R1 minus R2 divided by this is R square is actually multiplication of two R's. Here in this case R1 and R2, which is equal to Q by 4 pi epsilon naught. I am going to put these two below this R1 and R2 minus R2 divided by R1 R2. So this is the further simplification. So it become Q by 4 pi epsilon naught. Here This R1 and R1 will cancel, it become 1 over R2 minus 1 over R1, and this is equation 8. So this is the equation for the second step. The work done now from from the R2 to R3. So this general expression for the work done from the R2 to R3 is equal to this general expression, which is Q by 4 pi epsilon naught, and instead of del R, now I will write R2 minus R3. The R2 is greater than R3, therefore we can write R2 minus R3 divided by R2 R3, which is equal to Q by 4 pi epsilon naught, and this is become R2 divided by R2 R3 minus R3 divided by R2 R3. So it become Q by 4 pi epsilon naught, and this R2 is cancelled with this R2, it become 1 over R3 minus this R3 will cancel, it become 1 over R2, and this is the equation 9. This is equation 9. Now we will take large number of steps, and then we will reach to Rn, the last step. So in this way we will take large number of steps, and then we will reach to the last step, which is the work done from the Rn to Rb. This is the last step here. This is the last step. From this Rn, then we will go to this Rb. So the expression for that is this. Here is the general expression. From the general expression, Q by 4 pi epsilon naught. So this is actually 4 pi epsilon naught. Instead of del R, we will write Rn minus Rb divided by Rn Rb. Do the same calculation with this as well, 4 pi epsilon naught, and Rn divided by Rn Rb. Similarly, Rb divided by Rn Rb. By further simplification, it becomes Q is equal to Q, and this Q divided by 4 pi epsilon naught. Here Rn will cancel, it become 1 over Rb minus this Rb, and Rb will cancel, it become 1 over Rn, and this is equation 10. So these all are the calculation for, so we calculate this step, the work done for this step, then for this, then for this, and up to, and generalize it, and then we determine the work done for the last step. So we cover all these. So in order to find the work done from this Ra, from this point A to point B, we will add all that steps. So at the last we will add all these steps, and that's present in the equation 2. So now we will proceed this equation 2. So that equation 2 now become, here is that equation 2. So equation 2 implies that the work done from A to B is equal to the work done from A to B is equal to the work done from A to R1, and this is given by the equation 7. This is the work done from A to R1. So here I will put the value of this instead of this. So here I will write the value of this. So from the equation 7 we can say that we can write here that Q by 4 pi epsilon naught, and equation 7, 1 over R1 minus 1 over Ra. Here I will write 1 over R1 minus 1 over Ra. and the plus the work done from R1 to R2, which is given by work done from R1 to R2 is given by equation 8. So we will add plus equation 8. Equation this value is q by 4 pi epsilon naught and 1 over R2 minus 1 over R1 and then plus then we will add the work done from R2 to R3, which is present at equation 9. So here I will put q by 4 pi epsilon naught 1 over R3 minus 1 over R2. And we will take large number of steps and then we will reach to the last step, which is this. So the equation 10 here, we will put the value of equation 10 here, q by 4 pi epsilon naught 1 over rb minus 1 over rn. So this is equation 2. Now q by 4 pi epsilon naught is common in all these, so we will take common that from this equation. So here the work done from A to B, we can write this q by 4 pi epsilon naught is taken common. So here 1 over r1 minus 1 over ra remain, and then plus 1 over r2 minus 1 over r1 and this plus 1 over r3 minus 1 over r2 and then plus we take a large number of steps and then plus 1 over rb minus 1 over rn. So here this r1 cancel with this r1 and similarly this r2 cancel with this r2 and in this way this r3 will also cancel here with minus r3 and this minus rn will be cancelled and here will be present 1 over minus rn. It will cancel with that, and so here the remaining thing here will be work done from A to B is equal to this q by 4 pi epsilon naught, and here the remaining thing will be 1 over Ra, it will not cancel, and plus 1 over Rb. So here I can write this q by 4 pi epsilon naught 1 over Rb minus 1 over Ra, and this is the work done from point A to point B here in this is that work done from this point A to point B. Now in order to find the potential difference here at this point B, we will put the value of this work done from A to B as we calculated in this equation 1 and divide that by q, then we will determine this, then we will get this potential difference value. So here equation 1 implies that potential difference is equal to the work done from A to B divided by q. So here the work done from A to B is given by this, so we will put the value this value 4 pi epsilon naught into 1 over Rb minus 1 over Ra. This we put these R instead of here instead of this work done from A to B. This is the value of that, and these are divided by this q. So this q, sorry, I'm going to change the color here. This q and this q will be cancelled. So del V become del V is equal to 1q remain here divided by 4 pi epsilon naught into 1 over Rb minus 1 over Ra. Uh, from the figure, we can say that the RA is actually the distance between this positive source charge and this test charge. So we consider this test charge at infinity. Therefore, we can say that this RA is infinite. So here put the R instead of this RA infinity. So this become Q by 4 pi epsilon naught and 4 pi epsilon naught into 1 over RB minus 1 over infinity, and 1 over infinity is equal to 0, so it becomes del V is equal to Q by 4 pi epsilon naught and 1 over RB. This potential difference here this potential difference is actually VB minus VA. The potential at B is higher. Here, the potential at B is more as compared to the potential at A. And the potential at A is 0 here, as we discussed before, because this is present at infinite distance from this source charge. So here we put the value of VA 0. So instead of this del V, I write this VB minus VA and put this equation Q by 4 pi epsilon naught and 1 over RB. Now put the value of VA 0. So this potential difference is equal to, this becomes 0, it will become VB and Q by 4 pi epsilon naught and 1 over RB. 1 over RB. And this is the final equation for the potential at point B. This is the final equation. This is the final equation for the potential at point B. So at this point, the potential now defined, which is given by this formula. So therefore, in the previous case here, we can write the potential for each point. In order to find the potential at each point, we will consider the other charge at infinity, and with respect to that charge which is present at infinity, we will define the potential. So here, in this case, at this point we have potential. Similarly, at this point we have potential. At this point we have potential, and according to the formula, let's say potential is equal to work done per unit charge. So here the potential is the work done per unit charge, and the work done is actually the force into displacement divided by charge. So the displacement per a point is 0, therefore the potential is 0. But this is explained here. The potential at a specific point is not 0, because we consider another positive charge at infinite distance from this positive charge, and with respect to that infinite discharge, we will find the potential at a specific point, and therefore here this voltmeter show us the potential at a specific point. So in order to find the potential at a specific point in electric field, we will consider the other point at infinite distance from that point, and with respect to that infinite distance, we will determine the potential. So we will apply this last equation and we'll find the potential at that point. So this is the maths and the in-depth intuition of the concept of potential and potential difference. So that's it, guys. Thanks for watching.